Hello, community. You might say, hey, why you want to make small language model smarter? Well, just 2 days ago, I posted here on my community post here that I read here that Massachusetts Institute of Technology published OpenAI is announcing that its technology will be deployed directly on the battlefield. And MIT tells us here, defense contract completes here its military period. So, okay, December 4th, and then really the next day, it was here the second surprise by OpenAI that they now offer that we can pay OpenAI for their reinforcement fine-tuning of their O1 models in the first quarter of 2025. And I thought, we understand exactly what is happening here in this reinforcement learning-based fine-tuning because it was kind of invented here by Princeton and UC Berkeley. Now it is open source. So why should I pay this particular company that gets now here all the money here from a different source? And I decided here that I will not give them my money anymore. So therefore, here you understand why I suddenly have the topic, how to make small language model smarter. So you see, if I focus now more on open source AI models and therefore on smaller AI models that I can run here on cloud infrastructure like Lambda or other cloud providers, there is now a real simple question I have to answer: how to make a small language model smarter. So I use all my intellectual power and let's find a solution. So here we have here a survey on in-context learning here by Peking University, Hong Kong Polytechnic, and Carnegie Mellon here. And it is due to its zero training cost that I think this in-context learning, also known as a few-shot prompting, this has really gathered some attention here and emerges here as a promising approach to improve here the reasoning capabilities, especially of small language model. And I think this is a beautiful publication if you're interested in this, because the key idea is simply, if you think about the human, it is kind of an analogy-based learning, no? We say, hey, I give you some example and now come up with a solution that is kind of similar to the examples I have given you in my prompt. Now, it expects here these LLMs to discern hidden patterns from carefully curated demonstration examples, 1, 2, 5, 10, and subsequently generate here the appropriate improved reasoning step for unseen test problems. So, of course, you know that here, and this is another publication from University of Texas, Johns Hopkins University, and Princeton University, chain of thought here is a pivotal advancement here in the reasoning domain. And by incorporating the simple prompt, let's think step by step here alongside, and please do not forget those, the step-by-step reasoning examples you have to provide. This approach enables here our AI models, our small language model in particular, to kind of emulate here human-like reasoning processes. Now, in this publication here by NYU, large language models are zero-shot time series forecasters. We understood that language models appear to have accurately here the components to do this time series analysis, such as linear trends combined with seasonal fluctuation. The AI systems kind of somehow understand here the complexity of a time series forecasting. But of course, we also understand for this publication here, University of Edinburgh and another company, that we have here to be really careful here because ICL-based reasoning performance is highly contingent upon the provided demonstration examples. So let's talk about this for a second. This LLM was found out here, particularly in this very interesting archive preprint, exhibit here a high sensitivity to the task-specific characteristic and the multiple facets of ICL example that we provide in our prompt to the small language model. And this characteristic here include here the demonstration quantity, 1, 3, 5, or maybe 100, maybe 500. Then the ordering of those and the label distribution. You're not going to believe it, the effect of a label distribution on the ICL performance of small language models. So when our ICL encounters a reasoning task that shares similar logical structures, you think this is it. No, because if it differs here in the presentation format that we have here, the formal structure of the presentation in our prompt to our small language model, reconstructing now additional correspondingly structured demonstration example is sometimes really necessary. Because we want then to have an unseen task, but therefore we also have the same presentation format of our few short examples in our in-context learning to receive here the maximum benefit from in-context learning. Now, just yesterday here from OpenAI, the O1 system card, if you studied this, I've given you also here the hint in my community tab of my channel here, this chain of thought deception monitoring. And here OpenAI tells us, if the AI, and I say, if the AI is lying to you, if it's hallucinating and it's inventing incorrect facts, incorrect rules suddenly, such behavior could plausibly emerge from the O1 models here, the reward hacking during the reinforcement learning by human feedback, during this alignment step. And this is interesting because now OpenAI tells us there is a possibility, and I mean, if OpenAI tells you this here in the official documentation, you understand that it is not only a theoretical possibility, that optimizing our O1 models to prioritize here the user satisfaction could result those models here providing overly agreeable or inaccurate responses. So, reading this, I understand that whatever happens here in the reinforcement learning, in the alignment phase of our LLM, that the LLM behaves in a particular way, that we force the LLM to behave. And if we do this in a way that is not in coherence with the other data sets from the pre-training and the fine-tuning, then we're in deep trouble, because then we see here massive hallucination, or it could be theoretically a possibility that we have inaccurate responses. So what this means is that the quality of the pre-trained LLM, and in particular here the format, the data structure, the complexity, and the presentation of the pre-trained data set is from utmost importance, especially if we apply here a reinforcement learning algorithm where the data set is not coherent to the pre-trained LLM. So any incoherence we have now in the training data set between those two steps may lead to an increased hallucination because the LLM simply doesn't know what to do with those inconsistent data sets. Now, the same is true, and we already found this out, if you have a pre-trained LLM and you just fine-tune it. In the old times, we thought that we could fine-tune a model to a new domain knowledge. Today, we know that this is not possible. If it's not in the complexity, in the inherent domain structure of the pre-trained data set, the fine-tuning, it will modify nuances here, little details, but you cannot inject here complete foreign domain knowledge only by fine-tuning. The performance of the model will go down, down, and down. This also means that if you have here structural or complexity or theoretical incoherence here in those training data sets from the pre-trained to the fine-tuning data set, you have here an increased theoretical probability of hallucination happening in your fine-tune system or your reinforcement learning aligned system. And now you understand why in my last video where I talked about here Polygerma 2, the latest vision language model by Google, if you look, they give you here only the pre-trained model. And some of you ask me, hey, why suddenly we are back to the pre-trained model? Why not fine-tuned? Why not DPO aligned? What's happening here? Well, they did here, and if you read the documentation carefully, they have here a high quality pre-training data set. And they give you the details, and you see this in my video, on the pre-training data set. So we know exactly what the pre-training process included. And now we can start for our particular visual data set the fine-tuning process. We have to adjust this. Otherwise, the performance of our VLM will go down. And as you know, also, Google provided us with some fine-tuned version on particular visual data set, like for X-ray or for medical application. But those are highly specialized fine-tuned systems. And of course, as I showed you in the video, I or here Hugging Face also gives you here exactly the fine-tuning notebook how to do this. And you see here Polygamma processor, and from Google here you have Polygamma 2, the 3 billion pre-trained model only for 448 times 448 pixel. You see, this is now the insight that it seems that the industry is understanding, that we have to have a good pre-trained model, and then you build with your particular data set on this high-quality pre-trained model. Coming back to in-context learning, this is also really important for our in-context learning, because in this video I showed you here that ICL can outperform here fine-tuning or even RAG systems. And especially if you use some unsupervised ICL plus, like in this video, you get a real good performance out of this system. We have here this publication from, I think, Google DeepMind, yeah, completely, where they go here for many-shot in-context learning. So if you increase the amount of in-context learning, few-shot examples you provide, then the quality goes up. And Google writes here, we find that both reinforced and unsupervised in-context learning can be effective in the many-shot regime, particularly on complex reasoning tasks. So another indicator that this ICL is really, it costs nothing in the for the training data, for the post-training. We just have to find here the right adequate few-shot examples. And they say, you don't have to do the supervised ICL. If you do the unsupervised ICL, this means you just provide examples of the problem in your prompt to your machine, to your small language machine, without giving here the solution in the prompt, without giving the solution in the few short examples. This can improve your model performance substantially. And if you ask yourself, how is this possible? Even if there are no labels, no solution available, for common tasks like mathematics here, the mere presence of the relevant information may help here the small language model to cue here the skills in question, and answers will only be strictly necessary here, so the label data, if you have a task that is truly novel and was not at all part of the pre-training dataset. So, if you have a good pre-trained data and you use here unsupervised ICL, you just provided problems, but problems in the same complexity, or maybe in an increased complexity, because you remember the ordering is important here. You don't have to have all the solution. You don't have to have the labels to it, but the mere presence here of relevant additional information may help the system to come up with advanced reasoning processes, which is amazing in its own rights. Let's look at this publication here. It's called The Mystery of In-Context Learning here, a comprehensive survey on interpretation and analysis, and they go with a more mechanistic approach here. Highly recommend this. Also, it's already in version 3, so it's more than in the original paper, more than a year old. But it is highly interesting because they analyze here the effect of the pre-training data properties on the performance of the ICL. And they have a real deep dive into the pre-training data properties. And they demonstrate here that the LLM, so in our case the small language model, even more, they cannot perform here a new task through an ICL if the diversity of the pre-training task falls below a certain threshold. So, as I told you, the pre-training dataset, the quality, the diversity, the complexity, and even the ordering are of utmost importance here to have a good pre-trained model that we then can use in context learning for our particular task. And they found that there are 3 critical distribution properties of the pre-training data that drive here the in-context learning here. And particular, the investigated here the role of the induction head in our transformer architecture, and they show these are the crucial components for implementing here the in-context learning. And the induction head, they copy and propagate here the token patterns, enabling here the sequence prediction by leveraging a prior context. And they also found that models with deeper architecture or higher order induction head, which is quite complicated to build here in a small language model, but nevertheless we could maybe try to implement this on a single layer basis a little bit later in the architecture, demonstrate here superior in-context learning performance, reinforcing here the connection between depth and learning efficiencies. And if you're not really sure, hey, what is in a transformer architecture? What is this multi-head self-attention mechanism? And how does it relate here to these special heads? Short summary, the induction head emerges here as kind of a natural consequence, as they write in the paper, of the training process, of the pre-training process, when the transformer is exposed to data containing here repetitive patterns, even hidden patterns, or different associations on the semantic level. So induction head are just one of the many roles here an attention head can take on within a multi-head self-attention mechanism of our transformer, of our classical transformer architecture. If you want to learn more about this in-context learning, in particular the role of this induction head, I would say have a look here in March 2022, Anthropic published here, I think, one of the first main studies here. What are induction head? How could we detect that there is a specific specialization going on within a transformer architecture? And yeah, Anthropic showed us the induction head emerge as attention heads that specialized in recognizing patterns, coping with patterns, copying patterns, extending here patterns, and maybe even understanding here specific sequence of patterns. Now let's come here to another publication that happened just yesterday. This is here by Google DeepMind and UCL. And they now, and it's what a coincidence, no, that they now investigate here the broader spectrum of in-context learning here. They go in general for large language model, but I would like to focus here on the aspect of small language model with a little bit of modification, but rather easy. And they think about here how to improve in-context learning. You remember, 0 additional costs. We just need a good pre-trained model, and if you have a highly specialized domain-specific, then you fine-tune it a little bit, but otherwise ICL should be it, and it costs nothing. So this is now a really interesting application here for our next step. So they say adapting to task from instruction or role play. We're even extrapolating here the time series. We already talked about the time series. Instruction and role play. This is now interesting because this shines now some new light into the in-context learning mechanism. So highlight the importance of generalization, such as can be studied along several dimensions, not only the ability to learn something novel, but also the flexibility in learning from different presentations and in applying what is learned. So let's have a look. This goes here, if you know the term meta-learning, it's about 1-2 years old here, to our goal-conditioned AI agents. Google here is, of course, focusing also on an agent application specific, whatever. So in-context learning can now be categorized as an element of something bigger. In-context learning is the ability to use the context of early observation in a sequence task to support now prediction by our small language model or decisions taken by our AI agents later in that sequence, in the time series, in a way is that it is a meta-learned across here distribution of sequences. So you see, we bring here in-context learning under the umbrella of meta-learning artificial intelligence. And if we define now this sequence task to be any task at all involving making a sequence of predictions or action if we have an agent, based on a sequence of observations with our robotic friends, of course, here sensor input, then we are talking here about a sequence task. Now, the relation between the observation and the actions within and across this different time step evolve according here to a latent process. But we know this, no? The latent processes for each sequence are sampled from a real broad distribution that may have some universal consistent features, as well as some that might vary with time or with conditions. And this, you notice if you are a subscriber of my videos, you know this definition fits perfectly, what a coincidence, with the partially observable Markov decision process that we already examined in multiple of my videos here, especially here in the reinforcement learning regime and in language modeling. So you see, we have now, if you want, a new pair of goggles, a new pair of glasses we put on, and we understand that this in-context learning is here really connected here to our Markov decision process, where we know and we have all the mathematical formulas and the mathematical tools to operate with those. And now we apply it. So the full spectrum of this meta-learned in-context learning ranges here from a simple memory, like we have with our agents, so basic use of context to resolve linguistic dependencies, to supervised few-shot learning, and on to much more complex in-context adaptation of our small language model. And this is the beauty. This opens up here a gateway here to some more complex in-context learning, and maybe we even understand what is going on. Now, you remember we talked very briefly about instruction following, instruction learning. So this extends here the paradigm here of ICL beyond specific examples like input-output pairs in the few-shot learning regime to now complex scenarios where the model adapts to explicit directive or task description. So this means that now instruction following, if we see it here with this new polarization, doesn't depend on specific input-output examples for the task, but the model, the small language model, adapts now here based on the semantic of the instruction itself. So unlike here the traditional few-shot task that we provide in our prompt, where adaptation is constrained here to real specific examples in specific ordering in specific form with labeled data or non-labeled data, instruction following allows now for a more dynamic adaptation to entirely new task. And yes, you can feel the excitement because instruction following showcases how in-context learning here extend beyond the pure data pattern regime that we have currently to more abstract task description. And I think this is the way forward if we want to use the open source small language models and have a better reasoning performance on those models. And beautiful, we have finished the introduction, end of part 1. And tomorrow we will talk about the real implementation here of these new ideas, how to improve in-context learning for a better reasoning and causal reasoning performance of our small language model that hopefully are open sourced and we can use it locally.